All right. Here's a 2 by 2 system, a general 2 by 2 system. AX plus BY equals E, CX plus DY equals F. I want to find values of X and Y depending upon A, B, C, D, E, and F. Okay, first, let's use the solution by elimination. We'll rescale these so the Y's can't line up, and then add to cancel out. What we'll do, we have a BY and a DY, so we multiply the first equation by D, and the second equation by negative B, so you get BDY here and a minus BDY here. ADX plus BDY equals ED, minus BCX minus BDY equals minus BF. Now if we add the equations, these two terms add up to AD minus BC times X. The BDY minus BDY cancels out, and on the other side you get ED minus BF. So you get X equals ED minus BF over AD minus BC. Okay, for the second to solve for Y, we'll eliminate X. We have an AX and a CX here, so we multiply by a negative C and a positive A. And long story short, you get this. Y equals AF minus EC over AD minus BC. This is what's called a closed form solution. All you need to do is plug in the numbers and turn the crank, and out comes the answer. You don't have any, it's all like, I think of this solution as sort of like diagonal parking, whereas the one I just gave you is more like parallel parking, which is, you know, a lot more effort. The problem is, although it's a closed form, it's not immediately obvious what to write down. But okay, one thing is obvious. These are ratios of differences of products. And these products are kind of the same, EDBF, ADBC. AFEC, ADBC. Okay, so what we would do is we make a symbol for these differences of products, and those are called the determinants. So here's what we do. Remember I talked about a coefficient matrix, a 2 by 2 array of numbers. The determinant, which we denote by putting lines around it like this, the determinant of RSTU is RU minus ST. That's if you get rusty. So product along the main diagonal minus product along the opposite diagonal. And then in that case, with that symbol, we can define Cramer's rule. A 2 by 2 system is solved like this. AX plus BY equals E, CX plus DY equals F implies that X equals this ratio of determinants, and Y equals this ratio of determinants. They both have determinant of A, B, C, D. That makes it a little easier to remember. For X, what we do is we put the EF in the first column, E, B, F, D. For Y, and that's for X, the first variable. For Y, the second variable, we put the EF in the second column, AE, CF, over determinant of A, B, C, D. That's Cramer's rule. And I do believe I have a Cramer's rule extra credit set on the module, and you, of course, are welcome to do it. Let's see. 5.3. The advantage of Cramer's rule is it's a formula to remember, and once you have it, you can just put the numbers in and turn the crank. First, okay, some examples. What is the determinant of 2, 3, 2, 5? Well, okay. Product along the main diagonal, that's 2 times 5, minus product along the opposite diagonal, 2 times 3. 2 times 5 minus 2 times 3, that's 10 minus 6, that's 4. We have the determinant of negative 6, negative 2, 15, 4. Okay, negative 6 times 4 here, minus 15 times negative 2 here. That works out to negative 24, minus a negative, which is plus 30. Negative 24 plus 30, that's a 6. Now, here we have a 2 by 2 system. X plus Y equals 6, X minus Y equals 2. Well, okay, I already see here, it's 4 and 2, that makes sense. 4 plus 2 is 6, 4 minus 2 is 2. But let's solve by Cramer's rule. Put 1, 1, 1, 1 here in the denominator. 1, 1, 1, 1. Here and here, 1, 1, 1, negative 1. Okay. Now we put the 6, 2 in the first column for X, and then bring up the 1, negative 1 from below. We'll put for Y, the second variable, we'll put the 6, 2 in the second column and bring up the 1, 1 from below. All right, the denominator, 1 times negative 1 minus 1 times 1, that's negative 1 minus 1, that's a negative 2, which we'll put in for y as well. In the numerator, 6 times negative 1 is negative 6, minus 2 times 1, that's negative 6 minus 2, that's negative 8. Negative 8 over negative 2 is a 4. For y, put the 6, 2 in the second column, and you get 1 times 2 is 2, minus 1 times 6 is 6, 2 minus 6 is negative 4. That negative 4 over the negative 2 is 2. So the solution is x equals 4, y equals 2. Okay, once you get handy with the Cramer's rule, then, like I say, you just plug in the numbers and you turn the crank and you get the answer. It's no more of this back and forth and that can get confusing. This is really quite clear once you're familiar with the formula. Let's see. Here we have 3x minus 4y equals 9, x plus 2y equals 8. So the coefficient matrix is 3, negative 4, 1, 2. 3, negative 4, 1, 2, put its determinant in the denominator. Now for x, the first variable, we put 9, 8 in the first column, and then bring up the negative 4, 2 from below. For y, the second variable, we put 9, 8 in the second column here, and bring up the 3, 1 here from below. All right, let's see, and the denominators of both. 3 times 2 is 6, minus 1 times negative 4. 6 minus negative 4, that's a 10. So I have the 10 in the denominators for both. In the numerator, for x, 9 times 2 is 18, minus 8 times negative 4 is a negative 32. This is a double negative, 18 minus negative 32. That comes out to 50. So x is 50 over 10, which is 5. For y, 3 times 8 is 24, minus 1 times 9 is 9. 24 minus 9. That's a 15 in the numerator, divided by the denominator 10, that's 1.5. So the solution is 5 by 1.5. Now here we get to our singular cases where there's many solutions or no solutions. Here we have 3x plus 2y equals 11, 6x plus 4y equals 11. All right, the coefficient matrix is 3, 2, 6, 4, 3, 2, 6, 4. Put the 11, 11 into the first column for x. Here we go. 11 times 4 is 44, 11 times 2 is 22. That over 3 times 4 is 12, 6 times 2 is 12. You get 44 minus 22 over 12 minus 12. That's 22 over 0. Now, if you divide non-zero by 0, you get infinity. And that means that in this case, that these are parallel lines and there's no finite solution. Now now I'm going to making a problem almost the same. 3x plus 2y equals 11 and 6x plus 4y equals 22 rather than 11. So as before, we have 3, 2, 6, 4 determinant in the denominator. We'll put 11 and 22 here in the first column, so 11, 2, 22, 4. As before, the denominator is 0. The numerator is 11 times 4 is 44, minus 22 times 2 is also 44. 44 minus 44, that's 0. So the x is 0 divided by 0. That's the indefinite ratio, which can equal any quantity. So rather than these being parallel lines, these are overlapping lines which intersect along their entire length, and so therefore there are many solutions. So if you get non-zero over 0 from Cramer's rule, that means there's no solution. If you get 0 over 0 from Cramer's rule, it means there are many solutions. Three by three determinants. Now, there's the equivalent to Cramer's rule for 3 by 3 systems. And you need determinants for 3 by 3 matrices. Determinant of A, B, C, D, E, F, G, H, I. Well, okay. The book has a method where you break up the matrix into submatrices, and you get alternating sums of numbers times the times the co-matrix. And you can generalize that further for 4x4 determinants in a similar way, and 5x5 and 6x6. The problem is that when you get up to 4x4, it just gets like it gets a large number of terms, like 24 terms. 2x2 matrix, there's 2 terms. 3x3 matrix, there's 6 terms. 4x4, there's 24 terms. 5x5 is 120 terms. It gets way out of hand real quick. I think that for 4x4 systems and up, elimination is probably the best way. For 3x3, using matrices sort of works. It's a little troublesome, but it sort of works. Here's how you find a 3x3 determinant. You write down the matrix, then you write down the first 2 columns, ADG and BEH, outside of it, like this. And then you take products along downward going diagonals, AEI, BFG, CDH, here they are, and you add them up. Then you take the products along the upward diagonals, GEC, HFA, IDB, and you subtract them. AEI plus BFG plus CDB minus GEC minus HFA minus IDB. That's the determinant. Now with that definition of determinant, you get the I got that. The 3x3. Oops, sorry, that was the wrong one. You get the.
That's not true. Oh.
Yes? Oh. With that definition of determinant, you get a 3x3 Cramer's rule. So here we have this 3x3 system. AX plus BY plus CZ equals J. DE plus EY plus FZ equals K. GX plus HY plus IZ equals L. And X, Y, and Z are each of them ratios of determinants. And each of them you have the determinant of the coefficient matrix. A, B, C, D, E, F, G, H, I, here, here, and here. And for X, the first variable, you put the JKL in the first column and inherit the rest from below. For Y, the second variable, we put the JKL in the second column and bring up the other numbers from below. And for Z, the third variable, we'll put JKL in the third column and bring up ADG, BEH from below. Okay, so here are 2 examples of 3x3 matrices. 1, -4, 1, 3, 0, -2, 3, 1, -2, what's its determinant? All right, now I write the first column 1, 3, 3 here, the second column 4, 0, -4, 0, 1 here. Okay, so you'll take products along downward going diagonals and add them, and then products along upward going diagonals like these and subtract those. 1 times 0 times -2 here, plus -4 times -2 times 3 here, plus 1 times 3 times 1 here, minus 3 times 0 times 1 here, minus 1 times -2 times 1 here, minus -2 times 3 times -4. All right, so if you do the arithmetic, that's 0 plus 24 plus 3 minus 0 minus -2 minus 24, which after some turning gets you the number 5. Here's determinant of 1, 2, 0, 0, 1, 2, 0, 0, 1. What is that? Well, okay, I put the 1, 0, 0 and 2, 1, 0 here and here, right next to the matrix. And we take product along downwards and upwards diagonals. 1 times 1 times 1 here, 2 times 2 times 0 here, 0 times 0 times 0 here, 0 times 1 times 0, subtract it here, minus 0 times 2 times 1 here, minus 1 times 0 times 2 here. Okay, all these, almost all of them are 0. One of the first one is 1. So you get 1 plus 0 plus 0 minus 0 minus 0 minus 0. Okay, it's just 1. 5. Indeed. Yeah, this can be a little tiring. But I got to tell you, it's one of those things which saves you labor in the long run. At least for the 2x2 case, that's easy to remember. 3x3, like I say, it's a little harder. All right, we have here? Do we have an example? All right, I'm going to do one and only one 3x3 system. I assigned a few more in the book, but they're all basically the same arithmetic, same basic algorithm. But this is kind of tedious. Sorry. Here we go. X plus y plus z is 4. X plus y minus z is 0. X minus y minus z is 2. So we have the coefficient matrix 1 1 1 1 1 negative 1 1 negative 1 1. Put the 1 1 1 here. Put this 1 1 negative 1 here, and then do the determinant thing. First column, first diagonal 1 1 1. 1 times 1 times 1 is 1. 1 times negative 1 times 1 is a negative 1. 1 times 1 times negative 1 is a negative 1. Then minus the upper diagonal. 1 1 1 here, so minus a 1. Minus negative 1 times negative 1 times 1, that's a 1, so minus a 1. Minus 1 times 1 times 1 is a 1. So 1 plus negative 1 plus negative 1 minus 1 minus 1 minus 1 is negative 4. So we will put a negative 4 in all these denominators. Now for x, we put 4, 0, 2 in the first column. And 4, 0, 2, 1, 1, negative 1, add after the usual determinant stuff. 4 times 1 times 1 is 4. 1 times negative 1 times 2 is negative 2. 1, 0, negative 1 is 0. Minus 2 times 1 times 1, that's minus a 2. Minus negative 1, 4, minus a 4. Minus 1, 0, 1, that's a 0. So 4 plus negative 2 plus 0 minus 2 minus 4 minus 0 all adds out to negative 4. So x will be this value, this determinant, divided by this determinant. Negative 4 over negative 4, that's a 1. For y, we put 4, 0, 2 in the second column, like this. And then to evaluate this determinant, we put 1, 1, 1 column here, 4, 0, 2 column here. And then, yes, we go on product along main diagonal, downward diagonals. Here's a 1, 0, 1, that's a 0. 4, negative 1, 1, that's a negative 4. 1, 1, 2, that's a 2. Minus the upward diagonals. 1, 0, 1, minus a 0. 2, negative 1, 1, minus a negative 2. Minus 1, 1, 4, that's a negative 4. This all adds up to negative 4. So y will be this divided by this negative 4. Negative 4 over negative 4, that's a 1. For z, we put 4, 0, 2 in the third column here. And then we'll put this 1, 1, 1 column here, this 1, 1, negative 1 column here, and then take downward and upward diagonals. 1, 1, 2, that's a 2, plus 1, 0, 1, that's a 0, plus 4, 1, negative 1, negative 4, minus the upward diagonals. 1, 1, 4, that's minus a 4, minus negative 1, 0, 1, that's minus a 0, minus 2, 1, 1, that's minus a 2. After a bit of work, that comes out to negative 8. So z will be this negative 8 divided by the determinant matrix negative 4. Negative 8 over negative 4, that's a 2. So the solution is x is 1, y equals 1, z equals 2. All right, that we've done plenty. And I'm going to turn off the robot.